your whole equation, x cubed plus 2x. And you could have put parentheses around it and placed a 2 in front. Like that's how you would apply it to the equation. But you don't have to do that. You just have to know that if you have a 2 in front and you're multiplying it by f of x, it does the same thing to every graph. So does anybody know what that does to the graph, Dylan? Yeah, it makes it more narrow. So he said more narrow. We are going to call that a vertical stretch. So that 2 is making the graph more narrow, steeper, that would be another word, but it's pulling it vertically. Because the 2 is taking your y values and it's really doubling them. So instead of a y value being at 1, now it's doubled and it's higher at 2. So it's pulling it vertically. That's a vertical stretch. So 2 times f of x is really saying you're doubling your y value. The third one, we have f of negative x. That one's a little different. What are you doing with that? It's not shifting the graph. Josh, what do you think? And why do you think it's reflecting over the y-axis? You're right.
I just thought of it like f of x goes from negative 10 to positive 30. I just know you move from
So he said you're flipping it over the y-axis. Emma, can you add to like why you're flipping over the y-axis? Exactly. So what you're doing is taking all of your positive x values and now you're making them negative. So if you have an x value that is positive and you make it negative, you're flipping it over the y-axis. So x is becoming negative, therefore we're flipping over the y-axis. Questions on those three? So looking at the second group of problems underneath, instead of having it in function notation, it's written as an equation. So explain the changes that take place if I had y equals x to the fourth. How would these 4 graphs compare? And again, you can write it as a function notation, or we can just write it in equation form to see the shift in the equation form. So Lauren, with letter A, we have g of x equals x minus 2, and then to the 4th power. How would that change the graph? Yeah, so that minus 2, remember the minus is part of the formula, part of the equation. It's a positive 2. So that's moving right 2 units. So now it's actually in that equation form. But even if it was in function form, it would still move to the right 2 units. So this could look like g of x minus 2. That would be the function form. Means the same thing. Letter B, we have g of x equals negative, and then x to the 4th plus 3. So there are 2 things happening here. Brenton, can you give me one of the 2 things happening?
It is being moved up 3.
Yeah, so this plus 3 moves it up 3. Do you know what the minus sign does when it's in front? You know, Brenton?
Does it make it reflected in the y-axis?
It does reflect it.
The
It's over the x-axis. And the difference between this guy and the one above, if it reflects over the y-axis, you're going to have the negative directly attached with x inside parentheses. So it would say that the negative is directly attached to x. Right now, that negative is separate from x. It's like having a negative 1 and then the x to the 4th. So that one's reflecting over the x-axis. So your y values are being multiplied by a negative 1, so they're flipping downward. So there is a difference, and we're going to talk about that, like the location of the negative sign. Where is it located? Because that depends on the reflection. Letter C, we have 4x to the 4th minus 5. Carrie, what's going on there?
It's steeper, so it's a vertical stretch.
Yep, so steeper because of the 4. So vertical stretch, and
then it goes down to 5.
good. And then inside moves it right because it's with x. The outside moves it up. And then the negative sign that's outside.
Flip it into X.
How did you feel like you did with those after working through the homework last night? So before we go back to the actual graphing, there are a set of examples at the bottom that we might as well just do since it's at the bottom of the page, and then we'll flip backwards and go through some graphing problems. But my hope was that after you did some of the homework last night and the minimal bit of notes that we did yesterday, you could look at an equation and kind of explain what the numerical values in the equation do. So looking at the bottom, these are a little different, and it kind of combines the two above together, but part of your homework is going to look like this, where you're not actually doing any graphing, but instead you're just trying to rewrite an equation using function notation. So it gives us two different functions. One function is x cubed, the other function is the square root of x. It says to express each transformation using the f or the g. So we're going to try and express each as a transformation of f or g. And just to kind of go back, our goal is to write it like this. So to write it with function notation instead of equation notation. So that's the goal. So if I have an equation, can I take that equation and then write it as a function notation? So g is the square root, f is the x cubed. So Carrie, I think you have an idea what you're going to do with the letter A here. What do you think?
I was listening to Can I get a drink?
Oh, yeah, sure. You may go get a drink. Does anybody have an idea as to how you could write letter A as a function? Emma? Say it again. So she said f of x minus 4. So we're using the f function because it's cubed. So that's why I'm choosing f. So I choose the function based off of the type of equation we have. And then to write it in function notation, well, it's x minus 4 in parentheses, so we're going to keep it as x minus 4 in parentheses. So it looks exactly the same, that x minus 4 part, but the f part then says we're dealing with the x cubed function. So looking at the one underneath it, letter C, just going vertically here since we're still dealing with the x cubed function, see if you can write that as function notation. So instead of keeping it as an equation, we want to write it as a transformation of f or g. A lot of the problems you're going to see are going to be like written in function notation instead of equation notation. Josh, what do you think for letter C?
I said 2f in parentheses x plus 3 and then minus 1.
Great. So essentially, same equation, but you're taking the cube out because you're using the function f. So that implies that my original equation was cubed. It looks exactly the same, except the f takes the cubed out of the problem. So it's still 2 times my function f, x plus 3 says we're shifting left, minus 1 says we're shifting down. That's what it said as an equation. We just use the function f. Questions? Dylan, what do you think for letter B? The square root of x and then plus 7.
G of x plus 7
And where does the plus 7 go?
inside.
Is-
Outside,
Why outside?
because it's not under the square root.
Exactly. So when it's under the square root attached with x, it stays inside with x. If it's away from the square root, separate from x, then it stays separate when you write it in function notation. So you have your g function, because it's a square root. There's nothing happening with x, that's why x is by itself. And then the plus 7 outside. Reese, do you think you could do the last one?
Is it 6 minus g of x minus 2
Yeah, and where's that minus 2 go?
in the
In the parentheses. Any questions on that? Just kind of writing it in a different form. Just like saying y and f of x, writing it in a different form. Alright, so we're going to go backwards. And now we're actually going to look at some graphs. So we know what everything means. We're going to see if we can flip backwards through your packet. And I think my page says 14, but I don't know if your page says 14. 15, not 14? We're looking at the same thing. So I'm looking at where it says reflections. This is part 16. So mine's off there. So how would you describe a reflection? What does a reflection do to the graph? Connor or Colin? Sorry.
Like it moves across one of the axes.
Yeah, he said it moves it across the axes. What else could you say besides moving it across the axes? How else could you? What other word could you use for reflection? Symmetrical. Are you raising your hand to leave again, or are you raising your hand to answer the question, Harry?
Flip.
A flip, yeah. So a flip, you could say it moves it across an axis. You could say that it is a, what word did you say? Symmetrical. We could also say it's a mirror image, which is kind of like symmetrical. A flip is probably the most common word that you would think of. You're flipping the graph. You're flipping it down. You're flipping it left. You're flipping it right, depending on where it's starting. So if we have a reflection on the x-axis, so here's my graph. Guess I don't need it quite as big. If we're reflecting it over the x-axis, if it's up, it bumps down. So it's flipping. That happens when your function becomes negative, because really you're making the y values negative. I had positive y values. A negative f of x is the same thing as saying a negative y. So now I have negative y values. So my original function becomes negative, or my y values become negative. That's a reflection in the x-axis. If we have a reflection in the y-axis, show another little picture here. Make it look like this. Now I'm flipping it over the y-axis, so it's going to go in the opposite direction. And my x values that were positive are now negative. So my original function, all the x values are negative. So the difference of where the negative sign is located, if it's with x, it reflects over the y-axis because your x values are negative. If it's in front of f of x or with y, it's flipping over the x-axis because it's going down to the negative y values. So I think there are a couple graphs underneath. We have the square root graph, which I actually just drew. So let's draw that little square root graph to remind you what that looks like. That's the one that hooks to the right. Because it's a positive square root, so I can only have positive values hooking to the right. I'm going to make a couple of points. 9 and 3. So I just chose good numbers that you could take the square root of. I can take the square root of 4, which is 2, so I have a point at 4, 2. I can take the square root of 9, which is 3, so I have a point over 9 above 3. So looking at letter A, we have a negative and then the square root of x. So how would that change our original graph? Hannah.
It would be a reflection of the x-axis.
And that's because you're taking the answer and making it negative. Your answer is y. So I'm now making all of the y values negative. The negative is outside of the square root. So if I had the square root of 1, now it's negative 1 because of the negative. The square root of 4 is usually 2, but the negative is making it negative 2. So then letter B has the negative with the x. So this one reflects it over the y-axis. Because my x's are going to be negative. So if I have a negative underneath, I can't plug a positive number in because I can't take the square root of negative 1. But I can take the square root of a negative 1, which is why we're flipping it on the other side. So that my values underneath the radical remain positive. So what happens with the last one, letter C?
Be a reflection across the x-axis and once you right
You are halfway there. So it does reflect over the x-axis. But what direction does it move? Even though there's a plus underneath there, it actually moves left. So anytime you see a plus, every standard equation has a minus with x. So that plus is really saying x minus and then negative 2. So that negative 2 is moving the graph to the left. So it moves to the left 2. And then it reflects over the x-axis, so then it's going downward. Questions? So I believe there are 3 more problems at the top of the page. Oh, nope, little definition here. So we have something called rigid transformations and non-rigid transformations. A rigid transformation changes the location, meaning it shifts the graph. Or it reflects the graph. A rigid transformation does not change the size of the graph or the shape of the graph. So a rigid transformation is literally shifting left, right, up, down, or flipping the graph. But there is no size or shape change. So it doesn't get wider, it doesn't get more narrow. It's not spinning some way. It's just moving left, right, up, down, or it's flipping. So the order for rigid transformations, we usually say to work from the outside in. And that's because a reflection is when you multiply something by a negative number. And PEMDAS, multiplication, comes first. And then addition or subtraction go next. So you're working from the outside. If there's a negative outside, we're applying that negative first. And then you kind of look inside. So a negative is really multiplying your x's by a -1 or multiplying your y's by a -1. PEMDAS, order of operation, says that goes first. So looking at the 3 graphs underneath, so now this is that function notation. So we have f and then x minus 4. Our graph is x cubed. So what would the x minus 4 do to the original graph? Reese, how would that move the graph? Yeah, so that x minus 4 moves it right 4. So my original graph was started 0, 0. Now it's moving right 4. You're going to be all right. Reese, do you know what the graph looks like if it's x cubed? Yeah, So she drew that little graph that starts at the negative infinity, it comes up and hits the middle of the graph, and then it kind of spins the other way. So, something like that. The next one says negative f and then of x minus 4. So Dylan, what are the two things that would happen with this graph?
Would it move right forward? And it would reflect.
And how is it reflecting?
It would like swap sides.
So it would swap sides. Is it reflecting over the x-axis or the y-axis? Yes. And you say that unconfidently. So the reason it's reflecting over the x-axis is because my function is negative. The function is the same thing as the y variable. So it's flipping over the x-axis. So we're moving right 4. This side is going down. This side is coming up. And if it works for me. Oh, there we go. Uh-oh. Well, I don't know what that is. I was trying to get it to flip. Ugh. I know. Try this again here. There we go. It flipped. Did you see that flip?
It did.
It did flip. There we go. So there's my original. So the top part is now moving down, and the bottom part is flipping up. The last one, notice there's two different ways that it's notated, and this is the one that's a little confusing. I think there's one on your homework like this. This part right here says f and then negative x plus 4. Anytime you apply something inside the parentheses, it gets applied to all of the pieces of the parentheses. So when you look at this, half of you are going to say the graph should move left. But because of the negative being applied with the x, if I pull that negative out or away from those two pieces or two terms inside, that negative also gets pulled away from the 4. And that's the trickiest part when there's a number applied inside with x. Because if you multiply by a negative, you multiply all of it by a negative. So if the x is negative, that means the 4 was also multiplied by a negative number. So my x, if I pull that negative out and separate it, this graph is still moving right 4. Even though it looks like it moves left. So if you see a negative with the x, think about factoring that negative out. And then this is reflecting over the y. So if I go back to my original graph here, because it is shifting right forward, here's my flip. I'm now flipping it over the y-axis. Well, the graph ends up looking identical to letter B, even though the reflection part really was done slightly differently. So whatever was x, my x's are becoming negative. So I had a right one, up one, my x now is the opposite, even though it looks like the exact same graph of letter B. So I'm going to stop there for today because I want to talk to you a little bit about your homework. And your homework is in your packet, but it is not the next page of your packet, Josh, it is page 21. So if you flip to page 21, it's not the word problems, but if you look at page 21, there is a crazy looking graph at the top of page 21. And then you have that function notation. I don't know if that one's it. Too many. Nope, that's not it. That's it. There we go. So the directions say you have this graph, and the graph is just f of x. And it looks like a piecewise function. So we have a straight line, got this little curve that would be probably part of a parabola, and then we have that horizontal line. So it says, on graph paper, we're going to graph the following problems using this original function, and then I have asked you to label your graphs very well. Instead of labeling them, make a t-chart. So I think it's easier to make a t-chart than it would be to label each individual point, because then your graph has points on top of it, and it gets a little messy, not easily seen. So before we do the graphing part, I'm going to start you off with number 1. How would the graph shift for number 1, just based off of the function notation? Dylan, how does the graph shift? Right, so this graph should move left 3 units. So I'm going to make myself a t-chart to represent the points that are currently in the graph. And I ask for 4 points. And those points would be what we call the inflection points, where the graph starts, where the graph ends. So give me 4. And again, if you want to label it, you can. But I think it's easier and it makes the graph neater if you just place them on the side with the t-chart. So if I start on the left, I have a point at -2, 0. The highest point is at 0, 3. My third point moving to the right, we have 1, 2, and then 2, 2. So Dylan said the graph moves to the left 3. Algebraically, what would that do with your t-chart values, Tom? Yeah, it's going to affect the x. So here's my number 1. What do you have to do with all those x values, Colin?
You have to add 3, basically, so then
How'd you get them to move left? You're on the right track.
you would subtract.
Right. So you're going to take your x values and subtract 3 from them. Even though it says x plus 3, that's really x minus a -3. So if we want our graph to move left 3, I'm going to take those x values and subtract 3 from them. So I would then have a -5. Nothing happens with y because it's not moving up or down. My 0 is now -3. My 1 is now -2. And my 2 is now -1. These are the new ordered pairs. I want you to find them first, and then go to that beautiful graph paper that I passed out to you. That's wide box graph paper, so that makes your graphs a little bigger. You would then plot these 4 points and connect them like the graph that is shown. So your graph should look the same as the picture given, except now it's shifted to the left 3. Questions with that? So for number 2, you would do the same thing. Kind of think about how does it move, and then change your original ordered pairs with that shift. So so that would be the T-chart. And you can put the T-chart like probably on that graph paper right next to it if you want, or you can put the T-chart like you're right tiny. So you can put the T-chart right next to each one of these. Yeah, she doesn't quite write as tiny as you.
Hey.
But feel free to put the T-chart next to the number or put it next to the graph. But I'd suggest making your T-chart first, plotting those points, and then connecting it like the graph is showing. So all your graphs should look the same, but they're just going to be shifting. They're going to be questions. The other part of your homework down below, those 6 questions are like those first couple that we started with. You're just writing it as a function. So you're not doing any work there, you're just changing it to a function of f or a function of g. I'd like somebody to present for Monday number 4 and number 5, the last two. I have 2 4s here. Does yours have 2 4s or did I fix it?
They fix it.
I didn't fix it on mine. Okay. So number 4 and number 5. Dylan and Alyssa, you didn't do any of that, right? So Dylan, number 4. Careful with that negative x, Dylan. And Alyssa, number 5. Any questions with what your homework is? Good. Carrie, I hope you